Dear physics aspirants, right now I have the physics book of +2 level and the topic is current electricity. Within this topic, I would like to discuss the some subtopic, and the topic will be, before going to the topic, and George Simon Ohm will be introduced by me, because this person will very iconic person for this subtopic. German physicist. Time was 1787-1854. George Simon Ohm. Uh, German physicist, professor at Munich. Ohm was led to his law by an analogy between the conduction of heat, analogy given by a law, the name was George Simon Ohm. Conduction of heat. The electric field is analogous to the temperature gradient, and the electric current is analogous to the heat flow. So this law given by the George Simon Ohm. Ohm's law is here a basic law regarding flow of currents. Flow of currents was discovered by G.S. George Simon Ohm in 1828, long before the physical mechanism responsible for flow of currents. Flow of currents will be discussed by me, and when you will discuss, then Ohm's law will be required for your understanding. That is known as the Ohm's law. G.S. Ohm, George Simon Ohm, was discovered. Imagine a conductor through which current I is flowing, and let V be the potential difference between the ends of the conductor. Then Ohm's law states that V infinite I, or V is equal to Ri, where the constant of proportionality R is called the resistance of the conductor. The SI unit of resistance is ohm. SI units of resistance is ohm, and is denoted by the symbol. You will see here symbol this. The resistance R not only depends on the material of the conductor, but also on the dimension of the conductor. The dependence of R on the dimension of the conductor can easily be determined as follows. Consider a conductor satisfying equation 3.3. Here you will see to be the form of a slab of length L and cross-sectional area A. Figure 3.2 will provide you the information regarding this. You will see here. Figure is here, illustrating the relation between R is equal to PL by A for rectangular slab length L and the area of cross section A. This symbol is a special symbol under the Ohm's law. Here you will see so that the length of the identical slabs side by side, figure 3.2 will provide you the information so that the length of the combination of 2L, the current flowing through the combination is the same as that flowing through either of the slabs. If V is the potential difference across the ends of the first slab, then V is also the potential difference across the ends of the second slab. Since the second slab is, you will see L difference. Second slab is identical to the first slab, and then same current L flow through the both. The potential difference across the ends of the combination is clearly sum of the potential difference across the two individual slabs, and hence equals to V. The current through the combination of L is the resistance of combination RC from equation 3.3. And here you will see the RC is equal to V by I is equal to 2R, and VI by I is equal to R and the resistance of either of the slabs. Thus, doubling of the length of the conductor doubles the resistance in general. Then resistance is proportional to length. You will see the symbol proportionality. Next, imagine the dividing of slab into two, cutting it lengthwise, so that the slab can be considered as a combination of two identical slabs of length L, but each having the cross-sectional area of the A2 slab here 3.2 C. You will see here, the figure is here. For given voltage V across the slab, it is if L is the current through the entire slab, then clearly the current flowing through each of two half slabs is I by 2, since the potential difference across the ends of the half slab is V. I the same across the full slab. The resistance of each of the half slab R is R1 is equal to V by L I by 2 is equal to 2 V by I is equal to 2R 3.6. Thus the halving of the area of the cross section of the conductors doubles the resistance. In general, then the resistance R is inversely proportional to the cross sectional area. R is inversely proportional 1 by A. Combining equation 3.5 and 3.7, we have R proportional to inversely proportional to the 1 by R, and hence for a given conductor where the resistance of proportionality, here the symbol depends on the material of the conductor but not on its dimension, that is the PE. This symbol is called the resistivity. The symbol of resistivity you will see here. Using this equation, Ohm's law reads at V is equal to I by R is equal to I resistivity L by A, current per unit area taken normal to the current. I by A is called the current density, is denoted by J. The SI unit of current density are A by M square. Further, if E is the magnitude of the uniform electric field in the conductor whose length is L, and then the potential difference V across its ends is EL. Using these, the last equation reads, you will see the last equations, EL is equal to J and resistivity L is equal to J resistivity. Above relations of the magnitude E and J can indeed be in a vector form. The current density which I have defined at the current through unit area normal to the current is also directed along E and is also a vector. J and U triple sign is E by E. That the last equation of the written as E J resistivity, and J is equal to resistivity E, where this and this is called the conductivity. Symbol you will see here. Ohm's law is often stated in an equivalent form, equation 3.13. You will see here, and in addition to the 3.3, next section we will try to understand the origin of the Ohm's law and arising from the characteristic of the drift of the electrons. So we will meet in the next session with a lot more. The next discussion will be drift of electrons and the origin or resistivity, origin of resistivity. We will meet in the next session with a lot more. Till then, thank you. Thanks a lot.